Hello! In this video I want to talk about Markov decision process, specifically its stochastic case in scope of reinforcement learning. So maybe let's start with my motivation. I've started learning reinforcement learning some time ago, and I've basically decided to download the book. This particular book is by Sutton and Bartle, called Reinforcement Learning, an Introduction. And yeah, I have to confess that my statistics is not that great. In fact, it's very bad. And when I've opened this book, I realized that I don't understand anything. So I had to kind of learn some statistics. And in this case, I kind of view this video as a chance or a motivation for me to learn both statistics and reinforcement learning, at least this decision Markov process. And maybe question why I'm actually creating this kind of video. So in fact, there are a lot of cool resources that cover the topic of Markov decision processes, and actually they are very good, but very often they don't go into stochastic case. And in this case, when you open this book, you see that they deal in general case, which is kind of more advanced, and so I guess it's easier to become confused. So in a sense, as a beginner, I think it's it's beneficial that I actually see things differently, and maybe I have some questions which I try to answer to myself and motivate it, describe, get some intuition. So maybe my approach, my view of these things will help you. So as a kind of disclaimer, in this video we'll just pretty much go through only what you see on this page up until this, and including this page where I will show you how to basically what this equation mean, maybe how to derive it, at least how I understand it. Basically we won't go into meat of reinforcement learning, which would be Bellman equation and state values, state action values and such, but still whatever I will show you here, it plays an integral role. I would say, I don't know, it plays like, it takes like 70% of basically theory, or at least, well, you will understand, but I think it's very important to get a good grasp of this stage. So what we will do, I think I will briefly introduce basic concepts in statistics. You can skip it. Briefly tell you what is Markov process and how to extend it to Markov decision process, specifically deterministic and stochastic case. And then I will introduce this joint probability. I will show you some examples, one example in my code, which shows you how can this stochastic stuff can appear, basically. We will derive some stuff, and that's pretty much it. So let's start with I guess, elementary concepts. I will try to do it as fast as possible. But let's just say we have an omega. It's in some kind of space of events where we gather information about all the events. It's a list or a set, I don't know, probably a list because it can contain copies. And say we have events that are characterized by two parameters. Either something is A or not A, and it also may be B or not B. So in this case, let's say first event is A is true, B is true. Again, it can be, I will use like a tilde to negate. Let's consider that's a binary case, not A, B. We can have repeats, of course, and so on, right? And then we can ask, okay, we can draw some kind of space, and we will say that each event lives in this space somewhere, and all these events live in this omega. And we can ask basically what is the probability that I take one particular event at random, and what's the probability that this event will have property A. And well, actually, if I let all these events in which A are true migrate and cluster together, basically they will bunch up and create some kind of boundary that separates a space where not A live and the other cluster where A live. The probability will be simply proportional to ratio of this A to whole omega in kind of length of sizes, number of cases. Okay, so maybe we can, this is the basic definition through lengths. Maybe we can ask another question. Maybe let's redraw this. We can ask that, like, okay, let's cluster B's. Again, they will move, create some kind of arbitrary boundary, and then we can ask, okay, in this we will consider this kind of this will be our B space, and we can ask, if we examine all this B, let's cluster all the A's which satisfy, and we can ask what is the probability that we take some event from B, I don't know, and that event B will be like basically will satisfy A and B in a sense. Okay, in language of conditional probability, what you would write is, what is the probability that we get element that satisfies B, given that we explore only region B. Kind of region B is just an intersection of whole space with B, which is a trivial definition, of course, but kind of it's important to keep track of it. And so of course graphically we would say that, let's call this, it's a space where both A and B are satisfied, and let's call it A plus, I don't know. So naturally it will be the same definition of A plus on our isolated, basically, region of B. And well, intersection of A in this case is just intersection of all A's with B. So in this case I do this substitution. I can write bottom half as this, but again it's kind of trivial. Nope, I had to write B. So or in language of probabilities means A comma B, which means A and B satisfied, divided by probability of B itself. Or you can rewrite this expression in form of chain rule. Means that A and B satisfied if we sort of first filter like space by B, and then in a sense we will analyze all the A's on this filtered space. So I kind of think of it of that first term. It puts a constraint on the second term, and well, calculate probability on the constraint space. That's my, maybe it's wrong, it generally should be correct. The vibe is the same. So next, what we will need, we will use this. Of course, kind of basic definition of probability. Also, we may add expectation value, expected value. How will tell it? Okay, I will call it. It will be discrete, whatever. I don't know if it's the same A. Well, it's just A consists. If we have a button that basically we push and it executes some function that throws out some A from some kind of distribution. Basically, we will push this button a lot of time and collect the probabilities. But anyway, let's say that a small in A has the definition of all the A's in A's. Okay, so it's a weighted sum of all possible outcomes of A. The weights are set by this probability distribution. So it's general, it's always like A times some kind of P of A. That will be used a lot. And probably last part, we can talk about marginalization. I don't know if you can call it that. But basically, if you have joint probabilities, so it's all the tuples, basically, in our case, A's and B's, and we keep some kind of statistics on a number of events, and then we normalize all our statistics with respect to all events, and we get something like that. So marginalization means, although we have kind of data on joint distribution, so all the number of outcomes same when X was true and X1 was true and Y1 was true, and for all the others. So marginalization is just saying, although we have all this data, we can kind of view it only for, say, one random variable. So in this case, we kind of collapse the dimensions, and then we get all the data with respect only to one variable. And of course, it all still sums up to 1, because all events must happen. I probably can write it also. It was like probability of A BI BJ, I can write BJ. So it's a summation over one axis. And that's pretty much all we will need. Now we can talk about Markov processes very briefly. So Markov process is nothing else than some kind of random walk on the graph. between some states. So we kind of have S. It's a list of states, and then we have basically transitions between these states are determined probabilistically through just transition matrix entries, which are saying if I okay, probability of going from some initial state as Si to some final state as J. And it's a matrix, of course. If we have n nodes and states, then it will be n times n matrix. And of course we can expect that let's say we sum node A. If we sum up all the neighbors of node A, it should sum up to 1. So it should transition somewhere, even if it stays on the spot, which we'll not deal with. So in fact, Markov process is just described by number of states and transition matrix. It can be as simple as, probably I will talk about only simple, some kind of random walk, some kind of drunk dude who's stumbling left and right, and the probability he will stumble left or right is just described by some kind of distribution. So it can be like equally likely to stumble left or right, or something more difficult. Now the main property of Markov processes is that it has no memory. Even if you explore how this drunken man stumbles with time through states, but you should know that once he reached some kind of state, it doesn't matter how he got there. The next time step decision, whether he will stumble left or right, it will be the same, basically independent of history. And the second property is, even if he returns on this state later in time, it will still be the same probability. So in fact, this matrix, it's not time dependent. It's kind of, we won't use it, but it's still important to know. Maybe I wanted to add also one interesting fact. And basically you may think that, okay, this short memory is kind of downside. It's too simplistic to basically calculate anything, although you can calculate a lot of interesting stuff. In this case, it's like you can see it as a Brownian motion and calculate diffusion and such. So in fact, I will give you a silly example that maybe you do every day in your life. So you're in a state of hunger, and you're sitting in a living room, and then you, let's say you start with not hungry, and then you transition to state, this joint state, hungry in the living room. Basically your hunger, and you go to kitchen to satisfy your hunger, and you become non-hungry in the kitchen. Then probably you, in a sense, return to your living room. So this kind of simplistic model, when you simply transition one step at a time by, like, we can augment the state space in such a way that it will basically be more robust, more interesting. So Markov process simply states and probabilities that what important from state some I to state Sj. There's only you can transition only some via probability Pij, and that's the limitation. Now you can introduce your Markov decision process. It can be stochastic, or maybe for Markov process we can draw basically draw a diagram when we have some kind of state. It's a very simple diagram, Sj. And that's it. You have some kind of two nodes, and the transition is governed by Pij. So in Markov decision process, we get a new set of toys. That means we have again S and P variables, and then we have A and R's. A is for actions and R for rewards. So in a simple term, we can say that for once between two states, prior we could only transition via probability, and then suddenly you can transition via action, so-called, and in fact it can be multiple actions, different, that will still do your job. So in a sense, our probability, not, can I use it right now? I don't know. I can say that that our transition function is basically a function of I will call S as initial state, A action, and S prime some final state. So prior we only had in Markov process S and S prime, which was basically our transition probability. Not in this case. Even between same states we can do different transitions. That's one. And the other thing is that we have maybe with each transition we can associate some specific reward. And then I would say that this reward will be also a function of whatever we choose. If you want silly example, okay, let's go with less silly. Just some state 1, state 2, and you have option to, like your agent in the game has option to just walk, or he can do a backflip, and then maybe your associated rewards with this, that if he simply walks, nothing will happen. If he tries to do a backflip, he will break his neck. Okay. So in effect, what I showed you, it's a deterministic Markov process. And what it means that we just have either defined transitions or undefined transitions, and we have pretty much defined rewards. Reward can be 0 also. In fact, we can say that we can have some kind of storage vector, I don't know, list, whatever, and we will store all the possible rewards from it. Probably will be useful for later. So we kind of, if we're summing over all the rewards, I don't know, we can just sum, not explicitly show the list, but sum for all the rewards, and so it's easier to write. And probably we can do the same with actions, some kind of A1, A2, dot. Okay. Now we can ask what is stochastic MDP in so this is the definition in the deterministic case. So in stochastic, in fact, we can draw also the diagram, and it will be kind of twofold. I will say outright, whenever you take an action from some state S, it will basically probabilistically will guide you, transition you to one of many states. Well, in fact, it would be like you start from S, you select some action A, although you may have multiple, and this action will guide you either basically some other states. And in fact, we will have an associated probability of reaching state S. Then we write conditional statement that we were on the state S and used action A. This is one case. If you want an example, like there is a popular game for reinforcement learning called Frozen Lake. And basically we can say that since it's frozen, if your agent who's standing on some patch decides to move to neighboring tile, say using action A right, then the system will say, okay, you're at this state, you're using this action, but the system will basically decides whether you will end up in your right neighbor, because it say if the ground is slippery, it will say, okay, with small probability it will just transition you to the neighbor tile which is not in the same direction. So this is the idea behind stochasticity in selection of actions. But we can go deeper. Wait, there's more. Basically, once you get, however you get to this state, say S prime 1, then in fact we will receive a random reward from a pool of rewards. And then I can say that probability that you will receive some reward R, given that you were in the state S, took action A, and end up in the state S, you know, it's some kind of probability distribution. If you want some kind of analogy, you can say that, okay, in simplistic, I will tell you the full story. Okay, so you're in some kind of game, you see a tile and you see a pile of gold, and basically when you come to loot it at some state, whatnot. So deterministic case would be, okay, you hopped onto this plane, tile, I don't know. Well, in fact, we've defined it a bit differently. We said that kind of more general situation, but in general it would say, okay, in this particular sequence of events you got 100 gold. So in stochastic case, in fact, this will be not gold, it will be some kind of distribution. It will be number sampled from distribution of gold coins in OK, maybe it will be somewhere around 100 golds, but it will be distributed. So pile of gold doesn't mean all the piles of gold will have 100 golds. But there may be different tiles when there's a smaller piles, and then these piles also will have some kind of distribution. That means your vector of rewards, if we decide to punch them together, it will be 0, large pile, and a small pile, and so on. But still, actually, the associated values will be sampled from distribution. So what we see is a stochasticity in actions. This is stochasticity in actions, and this is stochasticity in rewards. Taking an action A from state S does not guarantee that you will end up on some S prime. It will be sampled from some distribution. Same as the reward. You don't have a guarantee, you will just get a sample. So this is the idea. Let's check. What can we talk about? Okay, the next what we can describe, if you have seen that we have some state, actions, target states, and rewards. Basically, the most basic integral part information about the system, probabilistic, would be to know a joint distribution for any values as a subset. Okay. And so on. You get it. And so basically, by manipulating this distribution, we can marginalize stuff. For example, okay, one thing that we may notice that this matrix, because we can store it in a matrix, similarly like we could do it in transition matrix, in case this will be a 4-dimensional matrix. So in fact, it's normalized. It's kind of described the probability of this huge joint event, and in the event space is basically filled with these 4 tuples of size 4. And it's kind of problematic. I think it doesn't make much sense, but still, like you can, you know, that these events are sort of independent in this huge space. You can say marginalize, like calculate probability of beginning in a state S. It's like something crazy like this, summation over all the stuff. But still, you can get some kind of useful information from this joint distribution. So in a sense, you can get other stuff like S and A and stuff. Still, simply by marginalizing, you can basically get anything from this if you know all the possible variants of these joint distributions, all the possible outcomes. Well, and the normalization, of course, if I say that I sum over all the actions, target states and rewards, that pretty much means that on the diagram I sum up all this stuff, basically what I selected. I guess it's easier to think if these rewards and such are not probabilities but actual events, then it makes more sense that we are summing all the events that at some point started from S, and then someone took connection A and such and such. But still, the idea of marginalization here is important. What's maybe kind of bothers me, that maybe it's not very useful even to have all this information, because in a sense there's no point comparing, say, summing up maybe probabilities that start from some state 1 ... and then add some other probability that started from S and something else happened, right? Okay, but I want to I can do some observations about this matrix that will maybe help us a bit. So in a sense, we can write this matrix as a chain rule. In fact, I have ordered these arguments in order what you can tell it's a causal chain, because it's clearly that we started from S, took some action, it brought us somewhere, and so on and so forth. So in effect, you can expand this matrix via chain rule. If you don't remember what I'm talking about, of course, in this case, we have joint probability in this case of 2 events, and then I can kind of set these constraints, examine the space, narrow down the space. So basically I can write probability that S state is observed. Then I can write probability that from state S someone took action A. I can go further and say that probability that you end up in state S prime, given that you took action A and were previously and took it from state S. And finally I can say that I got a reward R by doing this journey of choices. I think it's a valid kind of expansion, chain rule. But what you may notice, the different terms kind of describe different things, and they are controlled in a system by different entities. So in this case, for example, right part, last term in a product, probability of getting reward given that you this. Probability that you transition to S prime given this. So in fact, it's something that is controlled by environment. Now the probability that you take action given that you're in state S, it's something that is controlled by an agent. Well, on this stuff, I don't know what it is. Probability that you're in a state S, of course, it's some kind of environment complexity question, but generally it's not something that environment control. So ideally, it kind of doesn't even make sense in scope of RL ask this question. But what we see clearly that we have something, one half of this expression that is controlled purely by environment and other controlled purely by agent. Maybe my motivation is to actually extract this part, this both, because we can derive quantities explicitly about the system. And then agent will basically take action based on whatever he thinks. This is often referred as a policy. Agent will have some kind of understanding of a system distribution, which action to take from which state in a long term that will maximize his reward, but we will not cover it, but just that you have seen it here. So this ultimate information, this huge joint probability, actually can be split into agent and environment part. So maybe let's talk how we can get rid of it. Get rid of the agent and keep only the environment. So that's what I said, environment stuff. So actually if we condition this probability, joint probability, given that we are in some state S and A, it reduces simply into this expression. Well, here, because of course we are trying to compute intersection of something that already has these intersections, it's kind of trivial. And also just by this construction, you see it's some kind of, it's our general information, which is, it's a normalization factor. And then what we can observe, we just plug in our definition of this expansion, use chain rule here, cross some terms, and exactly this matrix, it will be matrix. it contains only information about the environment. So also what you can observe is that if you marginalize this probability, like if we look at it, we can tell what it means in words, but let's say I kind of don't have an intuition what it means. I mean, unless we examine our expansion, or part of our expansion chain rule. So in fact, we can see that if we marginalize over R, that means we will, in fact, this sum over what was a bit confusing for me is the question of normalization in general. But what I understand now, it's either by looking expression like this, is that when you have something conditioned, this probability will be basically normalized up to R dimension, if we are talking about keeping these probabilities in the matrix. So in fact, yeah, if we just marginalize over R, we get expression for a transition probability. Well, I cannot give you like proper interpretation of why it's so, other than we just have this matrix that of joint distribution conditioned that is just so, it's just formulated so specifically that this holds. So in fact, at this point it's just a math question. And it's worth noticing that if we continue, if we now marginalize this expression over S prime of the possible states, again, given we have some kind of transition matrix, there's just no other option than for all transition to sum up, probabilities for all transition to sum up to 1. So it's kind of normalized up to last two indices. Probably what you can tell from here. There's some alternative ideas how to view it. Now I will show you an example. Basically, I don't have an environment, I have just a simple graph, 6 nodes, and basically agent can move between nodes, but in fact all these transitions, they are not associated with different actions. In fact, what I try to say is that I can only issue either move left or right. So in fact, when you see a transition that from 1 basically goes to 2 or to 3, that means that with some probability, if I say move to the right, with some probability it will land either on 2 or 3, and that's exactly the stochasticity of action that we've been talking about before. And again, you can see it in for different nodes. So in order to do some calculations, of course, we have to store these probabilities in some kind of matrix. It's very natural thing to do it, I think, given that we remember that we had transition matrix and Markov processes. So, okay, how can I do it? Basically, I have to define distribution of rewards, and I have to define distribution of basic target states based on actions or and initial states. So, and then my idea is that, okay, rewards for jumps will be simply proportional to distance. If I jump from node 1 to node 2, I get reward 1, 2 to 5, 3, and so on. But then I kind of want to introduce stochasticity between different basically outcomes of S prime. And I say that a probability of longer jumps is smaller. That's my setting. Again, it shows you that there is some stochasticity. So if we talk about the rewards, as I said, it's proportional to distance. Basically, I will have kind of a matrix for each row which associated with distance starting from 0, which doesn't happen, but still, in general case, a row is a distance and columns are basically rewards. So here's an example. Of course, distance in effect, it's a function of S and S prime. And originally we had the definition such that it can be a function of SA and S prime, but now it's kind of action independent. Again, distances is basically positive. We kind of don't differentiate inside each action. And so yeah, it ends up that our probability of receiving a reward is a function of starting and end point. And the distribution is such the chance to get reward 0, given that you made a jump of length 0, is basically 1. And then we start exploring, if you made the jump of length 1, then you will 60% get a reward of 1, 20% minus 1 reward, I guess 0, or 20% 2, and so on. So now the question about transitions, as I said, I want to kind of make it kind of inversely proportional to distance to make number of events less. And so I define just some random stuff that just works. So in this case, again, we don't have distance 0, but it will be normalized anyway. It just the longer the jump, the lesser the probability. So now we can think how we can construct these probabilities, and we just have definition in front of us, part of our chain rule, and it says we just have to multiply the distribution over R's and distribution over S primes. So you can interpret it as for some S in A, we'll have some kind of matrix, and this matrix will hold basically probabilities in such fashion. Here will be rewards, here will be S primes, target states, and basically there will be some distribution or rewards. In this case, S1 prime, S2 prime. A bit more complicated, but still. And we know that these distributions, which are P of R, SAS prime, they are normalized just by definition. And then I can do basically what I'm doing. I can multiply what I'm doing. Jeez, just a habit, strange habit. Okay, whatever. I can also have some kind of normalized distribution of S prime given S and A, and I will just basically multiply these rows of distribution over R times distribution over S primes given SA. Of course, it will be basically this matrix normalized. You can imagine that we have a sum of 1 here, sum of 1 here, sum of 1 here, and then we have some kind of weights. That will basically it will end up, it's just 1 times probability of something of state, and this will be also 1, and we will have total probability of 1. Okay, it will be row normalized. It's just my approach in this case. Unfortunately, we don't have this one probability distribution for everything. It will be easier in our case we have different number of target states. For example, node 1 will have probability of reaching, if we take action to the right, it will not reach 0, it will not reach 4 and 5. So kind of we have to recalculate these probabilities with normalization. We have to throw all that what's not happening and then renormalized. So kind of there's a lot of code for it, but the idea is such. So in this case, what I end up, get a slice of this matrix. I am in a state S. I'm just testing some entry node 5 and action 1, which is to the left in my case. And it will show me the probability of getting rewards after this transition, after reaching this state. So we can see if we for 5, it will reach 4. With some probability it will obtain most rewards of 1, but then it can also reach state 3. And with some probability obtain reward R2, but this longer jump, it has a lower probability, simply because it was multiplied by a value here versus here. In fact, I can marginalize overall last two entries, which are S prime and R. In this case, with matrices, I just do summation over second to last and last axis, and of course I get total probabilities. We can see that action to the right from state 0 has probability of 1, but it will not reach anything. Probability of to the left, probability of reaching some other state is 0, and similar thing on the last state. Now we kind of created this normalized matrix, and we can test if we can actually recover these probabilities using, although we have defined it using these probabilities, but the question is, can we basically recover it? So we take this expression for R, divide both sides, we get this expression, and we know we have to marginalize it over R, which we do. So I don't know why I have it here. But okay, let's go with the flow. Basically, that's what I want to recover, and I do what they ask me to. I have to check it, why it's so. Okay, I will think about it a bit later. So anyway, I marginalize over last dimension, and I actually extract the distribution that I've defined. So in fact, you can see that they are also row normalized. In fact, that means that we've uncovered a proper. Oh, I know what I did. It shouldn't be a box. So in fact, I plug this. This is our definition, and I plug this bottom half. So I calculate the bottom half, PS prime given SA, and I divide our big matrix S prime R given SA divided by this, but since we have like a lot of zeros everywhere, I have to specify where to do it, and I replace it with zeros elsewhere. That stuff. We recover properly the probabilities from our, that means our S prime R given SA matrix is defined properly. And now we can start actually calculating stuff for our environment. So we can calculate expected reward for this triplet. Now, what does it mean? We had a triplet S, A, S prime, and we want to calculate what is expected reward if we reach this state. Now we use expected reward because we actually have a distribution of possible rewards. So in a sense, for this state, S prime 1 and whatever, or whatever, we have to calculate a weighted sum of all the rewards given the probabilities that we actually achieve this reward. And that's what we do. We can define it as expected value of well, I don't know how to write it. Actually, I don't know, yeah. Let's skip it. But it will be a sum of our R's times probability of getting R, and then we write all this conditioning. We can either know this matrix because we've used it in definition. We didn't use it in definition. In fact, what we have to do we have calculated it just the last step. That's cool. So, okay, in fact, we just have to do this multiplication. But if you can notice that just by the structure of how we pack probabilities and rewards, it's nothing else than multiplying our P matrix by rewards. You just can write it in terms of matrix dimensions. Just, well, S in here is kind of length of S, our dimensions of matrix R. We just straight up multiplying by some R, which is a reward vector. And it will basically calculate dot product. It will broadcast the dot product of some kind of Ri times P. PR is equal Ri. sum over I calculated for all the entries of SA, S prime. There's some stuff I have to do with dimensions, because we're kind of constructing one dimension, but then we have to normalize stuff. And that's what we get. Expected reward for taking action S from S that brings us to S prime. And basically, yes, we calculated expected rewards because of stochasticity in reward distribution. What we can see for this particular example of node 1, that if we take action of right, the expected rewards on state S2 is 1, simply because of jump of length 1, and expected rewards of S3 is 2. So although I kind of reduced the chance of transition, but it received higher reward, so in fact it got higher reward. So what we get next? What do we do next? In fact, what we do, we can return to our diagram, and we can calculate now basically reward of taking action A from state S. So in a sense, we have calculated expected values of states, at least in the sense of instantaneous reward. And now we have to basically do expectation over this layer, which of course includes all the previous. And it's also easy to understand. We just say that we sum over states that you can reach via action A. You took an action and it can bring you to different states, and these different states will have different expected rewards. And you have to basically calculate it via actually this probability, which is also available for us. Available because we have calculated it previously. So in the sense that we calculate an expected value of doing this triplet, and the weights are the probabilities of transitions. Since we have calculated this previously, we can see if we plug everything in, we can cancel two terms and we will be left with this expression. Now maybe we will not go right now, later further. We just can examine what the Sutton and Bartel said. So basically we see the same definition of contracting over R to get distribution of transitions. This triplet is calculated exactly the same. And now the basic instantaneous value of taking action A from S is also the same. So it kind of proves the point that we are moving in the proper direction. Well, it's a bit harder to calculate it. Last time it was convenient to matrix multiply, but it's not apparent how to do it here. Although we clearly know that this is some kind of matrix, and we are doing something with entries of our reward vector. So we can rewrite it. In effect, here I ignore just first two dimension, the conditioning. I rename the S prime to S, but still you can just see here the matrix multiplication for some element. So that means that what we end up with, we're just summing over the elements of some kind of matrix times vector multiplication. And that's what we do here. It's very simple. Matrix multiply, sum over S primes. And we should get the basically value of a state action. You can see from 0 again, you're pretty much guaranteed to get 1 if you move to the right, because there are no options. And also the reward distribution is symmetric around 1. And rewards grow symmetrically around it, -1 and +1. And then as expected from S1, if you move to the right, you expect more than 1 because you have a chance small, but to transition to 3, and so on. You can repeat it, observe the same situation like here. So it pretty much was what I wanted to tell you. I'll go further into policies and such, but what we have found out is how to calculate the, well, generally what's most important is to calculate the reward of taking action in S prime, because it's kind of independent of an agent, and that will always be used. So in the case we can examine Bellman's equation, in case it's it's a value iteration procedure, but still it's a Bellman equation. We see all the same stuff, that we want to calculate the next reward from state S, and that reward would be based on how agent thinks which are probabilities to move are more profitable, but it's not important for us. What we're focusing on is this summation over S prime and R times R. And exactly this part describes first expected next reward. Basically, we have calculated this expression. And kind of that's it. I think it's the root of this whole expression. Now the value of a state and such, it will pretty much be derived from what we have calculated right here. Well, I hope my explanation will help you, and maybe I will do another video on a more in-depth something. But yeah, thank you for listening.